this video is pretty closely related to a previous video in using qualitative means to determine the relative strengths of acids and bases. Because you may want to check out that video before watching this one. It's also fairly closely related to a previous video where we predicted the position of equilibrium based on pKa values. In this case, we're going to do it using uh, the structures of the bases on the reactants and product side. So if I want to consider a particular acid-base reaction, right, there are two ways that I could use to predict whether uh, the reactants or products are favored. Right, I can use pKa values, right, and if the pKa of the acid on the reactants is stronger than the pKa of the acid on the products, right, then that's going to force the equilibrium to the right. Another way we can do it is by comparing the relative stability of the bases, and we'll do this the same way we did in the previous video. And in this case, the more stable the base is, that side is going to be more favored at equilibrium. So if B minus is more stable, then reactants are going to be favored. If A minus is more stable, then the products are going to be favored. So if we look at an example, I'm given this acid-base reaction. I want to know whether reactants or products will be favored at equilibrium. And so I think you can see, right, in this reaction, the NH3 is acting like a base. I'm sorry, it's acting like an acid, right? It's donating an H plus to the reactant on the left. So this is the acid, this is the base, right? So this is the conjugate acid and this is the conjugate base. So it's the two bases that we're comparing. So I'm comparing, is NH2 minus more stable or is this compound more stable? And so again, we use ARIO, right? So I've got the two bases. I use ARIO, right? So first I look at the atoms, right? And so I've got a negative charge on a carbon versus a negative charge on the nitrogen. So I think, right, our first criteria is what we're going to use to decide which one is more stable. So they're about the same size because they're both in the same row. So then we go to electronegativities. Nitrogen is more electronegative than carbon. So this base is more stable than this one. So the side that has the more stable base is the side that will be favored at equilibrium. Right? Another sort of similar way they could ask sort of the same question is whether a particular reagent would be suitable for accomplishing a particular task. And so we want to know, can we protonate this compound using water? So if I look at my reactants, right, so I've got that compound is going to react with water. If I'm trying to protonate this, then I'm trying to add a proton to it. So I'm trying to use water to act like an acid and donate the proton to this compound. So if we look at our mechanism, right, the base is going to steal the proton, right, and then these electrons will become a lone pair on the oxygen. And so our overall reaction should look something like this, right? And again, uh, this is the base. The OH minus is the base on this side, and so I want to see which one is more stable. Is OH minus more stable, or is this base more stable? And again, atoms, resonance, induction orbitals. I think atoms can be used to determine which one is more stable in this case as well. So nitrogen and oxygen in the same row, so they're about the same size, right? Oxygen is more electronegative than nitrogen, and so this base is more stable. So products will be favored. So when I mix these two compounds, they will turn into products, and so water can be used to protonate this compound. If we had decided that the reactants were more stable, then the answer would have been no. So one more example, right? Can I deprotonate this compound using NH2 minus? And so here are reactants again. And so now I'm trying to deprotonate this. So this one is going to be giving up or donating the proton. So in this case, this is acting like an acid. This is my base. So when I draw the mechanism, right, the lone pair on the base is going to attack the proton. These electrons will become a lone pair on the carbon. So my overall reaction looks like this. And again, I'm comparing the bases. So I've got the base on the reactant side, the base on the product side. And again, I go to ARIO. I think the atoms again will tell me, right, carbon and nitrogen about the same size. So I'd rather have the negative charge on the more electronegative nitrogen than on the less electronegative carbon. So in this case, this base is more stable. So the reactants are favored. And so, as I said before, if the reactants are favored, then no, NH2 minus would not do a good job of deprotonating this because we're going to have mostly reactants when this reaction comes to equilibrium.